areas of differential geometry. That means where we will use differential geometry in real life. Just hold a second. Yeah. So today's topic is effective areas of differential geometry in real world. So basically differential geometry is that mathematical discipline in which we study the geometry of smooth shapes and smooth spaces. Otherwise, it is known as smooth manifolds. It uses the techniques of differential calculus, integral calculus, linear algebra, and multilinear algebra also. Indeed, we can say that differential geometry is not only the standard language used to formulate general relativity, but it has found applications also in medical imaging, computer vision, Hamiltonian mechanics, geometro-thermodynamics, geometric design, geometric control, information geometry, navigation, GPS, and so on, and recently in machine learning also. Basically, differential geometry helps us in deciding what materials to use, what design to make, and also plays a vital role in construction. And buildings are built in different geometric shapes to give a new look, as well as to provide proper ventilation inside the house. So we can say that differential geometry has wide application fields in all areas. The outlines of today's presentation: introduction, then we will discuss the different branches of differential geometry, basic definitions, and effective areas of differential geometry where differential geometry is in process, and then references. So differential geometry starts in late 19th century. Differential geometry arose and developed as a result and in connection to the mathematical analysis of curves and spaces. Basically, what has happened, mathematical analysis of curves and surfaces have some of the nagging and unanswered questions that appeared in calculus, like the reasons for relationships between complex shapes, curves, series, and analytic function. Then we introduced differential geometry. So these are some of the branches where differential geometry is used. So there, as you have seen in the screen, there are so many branches of differential geometry. So let's have a look. First one is Riemannian geometry. So Riemannian geometry studies Riemannian manifolds, smooth manifolds with Riemannian metric. Basically, this is the concept of distance expressed in means of smooth, positive, definite, symmetric bilinear form defined on the tangent space at each point. It generalizes Euclidean geometry to spaces that are not necessarily flat, though they still resemble Euclidean space at each point infinitesimally, or we can say that in the first order of approximation. Second one is pseudo-Riemannian geometry. So pseudo-Riemannian geometry is nothing, it generalizes the Riemannian geometry to the case in which the metric tensor need not to be positive definite. Then the next one is Finsler geometry. So basically, Finsler geometry has Finsler manifolds as the main object of study, and this is the differential manifold with a Finsler metric, that is a Banach norm defined on each tangent space. Then the next one is simplicity geometry. So in simplicity geometry, we study the simplistic manifolds. At most, simplistic manifold is a differentiable manifold equipped with a smoothly varying non-degenerate skew-symmetric bilinear form on each tangent space. Then the next is contact geometry. So basically, contact geometry deals with certain manifolds of odd dimensions. It is very close to symplectic geometry. Then complex and Kähler geometry. In this geometry, we study the complex manifolds. Then on the next line, it's CR geometry. CR geometry is the study of intrinsic geometry of boundaries of domains in complex manifolds. Then conformal geometry. In conformal geometry, we study the set of angle preserving, that is also known as conformal transformation on a space. Then the next one is differential topology. In differential topology, we will study the global geometric invariants without a metric or symplectic form. Then Lie groups. In Lie group, as we know that Lie groups is a group in which the category of smooth manifolds lies. Beside the algebraic properties, this enjoys also differential geometric properties. So in Lie groups, we will study the group in which smooth manifolds lie. Then geometric analysis. Geometric analysis is that mathematical discipline where tools from differential equations, especially elliptic partial differential equations, are used to establish new results in differential geometry and differential topology. And the last one is gauge theory. So gauge theory is concerned with the study of differential equations for connections on bundles and the resulting geometric moduli spaces of solutions to these equations as well as invariants that may be derived from them. These equations often arise as a Euler-Lagrange equation describe the equation of motion of certain physical systems in quantum field theory, and so their study is of considerable interest in physics. So first we will discuss some basic definitions that are related to differential geometry. First one is space curves. When we are talking about space curves, so we have to know how we can express the parametric equation of a curve. You have already studied about the curve, so the equation of curve is directly represented by RT equal to XTI plus YTJ plus ZTK, or simply we can write R equal to XYZ. A space curve can also be expressed by the intersection of two surfaces also, where the equation of the surfaces are in the form F1 XYZ equal to 0 and F2 XYZ equal to 0. Then three fundamental planes are very important in differential geometry. First one is tangent plane. So basically what is tangent plane? We know that if, as you've seen in the picture in this figure, if S is a surface and we have to find out the tangent plane at a particular point P0, whose coordinates are x0, y0 and z0, then P0 contains all the tangent lines to the curves SS. So all these tangents lie in that plane. That plane is called the tangent plane. So basically tangent plane to the surface contains all the tangents lying to the curves in S that passes through P0. Then a normal plane. So a normal plane is any plane containing the normal vector of a surface at a particular point. We know that normal vector is that vector which is perpendicular to tangent plane. So we can say that normal vector is that vector that is perpendicular to tangent plane. And then principal curvatures. So the two principal curvatures at a given point on the surface are basically the eigenvalues of the shape operator at that point. They measure how the surface bends by different amounts in different directions at that point. So these are the three planes: rectifying plane, osculating plane. So rectifying plane means, as you see in the figure, at point P0, rectifying plane, this is the curve C, which has shown with blue line. Then the rectifying plane of C at particular point P is the plane spanned by binormal, that is denoted by B, and tangent, that is denoted by capital T in the figure. Similarly, if we are talking about osculating plane, so osculating plane of any curve C at point P is spanned by the tangent, that is denoted by T, and the normal which is denoted by N at T0 with normal vector B0. So there, as I have told earlier, there are three fundamental planes in differential geometry. First one is osculating plane, normal plane and rectifying plane. As you have seen in this figure, in osculating plane is the plane passing through a point P and it is perpendicular to binormal B. It means if we have to find out its equation, then it is given by R minus R dot B. B is binormal vector is equals to 0. Since this plane is perpendicular to y normal, it means its dot product is 0. So its equation becomes r minus r dot b vector is equals to 0. Then normal plane. So the equation of normal plane can be obtained by r minus r dot t is equal to 0. It means dot product of tangent vector and r minus r. Why? Because normal plane is perpendicular to tangent. It means the dot product of normal plane and tangent vector is equal to 0. Then we are talking about rectifying plane. So rectifying plane, as you have seen in this figure, rectifying plane is perpendicular to the principal normal. It means its equation becomes r minus r dot n vector is equals to 0. It means dot product of principal normal to the point is equal to 0. We all have a familiar notation of gravity. It causes apple to fall and the moon to orbit the earth. So the idea of gravity was first proposed by Isaac Newton in 1686 to the Royal Society. Newton proclaimed with his theory that the force pulling the apples to the ground and keeping the moon in the orbit around the earth were one in the same, but he had no idea what this mysterious force actually was. It was not for another 250 and so many years until this mysterious force could be somewhat understood by Albert Einstein. Einstein is the most well known by the general public for his famous equation E equal to mc square. We all know that. However, it is arguable that one of his best pieces of work was that of general relativity, in which he came up with the Einstein field equation. Although these equations may appear daunting, they allow us to show that the space and time in which we live isn't simply an empty void. It can be bent and stretched by a stuff within it. Massive objects such as stars and planets bend the space and time around them. And any object that passes through that curved space-time will move as if being pulled as a force, which is what we experience as gravity. But if we think, how did Einstein show that objects actually curve space-time? It is easy for us to know if an object is curved or not require some clever mathematics known as differential geometry. This investigation examines the differential geometry and other mathematical ideas behind Einstein's theory of general relativity. It explains how the curvature of space-time is deduced, how objects move in that curved space-time, and how the objects themselves curve space-time before bringing it all together in the Einstein field equation displayed above. Yeah. So to begin investigating the differential geometry behind general relativity, the notion of the manifold will be introduced, which will provide the necessary framework for curved space. Indeed, one such idea which is essential to general relativity is that space-time can be thought of a four-dimensional manifold covered in a series of coordinate patches. As a matter of curves in space-time, the geometry of such a structure is curved and therefore it is non-Euclidean. So these are the applications given by Einstein with the help of differential geometry. This means that some ideas that seem simple in flat Cartesian coordinates need to be upgraded. And such an idea of distance and inner product and parallel transport of vectors, this can be done through the use of metric, which this investigation aims to adequately describe. In relation to this concept, it should be pointed out that as a coordinate system is simply a means of labeling points in space-time. Any physical laws should be independent of the coordinate system. This then will bring us to the idea of tensors and their transformation laws, which have a property such that they allow you to write equations which are coordinate invariant. So one of the most important application of differential geometry is in theory of relativity. Then the next one is, what is GPS? So all of us known as GPS is a global positioning system, which is a global navigation satellite system that provides us location, velocity, and time. And GPS is everywhere. It works in your car, your smartphone, your watch, and it helps us where you are going from one point to another point. A GPS receiver, as you have seen in this picture, in this figure, a GPS receiver operates by a user on Earth, measures the time it takes radio signals to travel from four or more satellites to its location. It calculates the distance to each satellite, and from this calculation determines the user longitude, latitude, and altitude also. So the principle behind the unprecedented navigational capabilities of GPS is triangulation. So what is triangulation? I will discuss. So to triangulate, a GPS receiver precisely measures the time it takes from the satellite signal to make its brief journey to Earth, less than a tenth of a second. Then it multiplies that time by the speed of radio waves per second to obtain the corresponding distance between it and satellite. This puts the receiver somewhere on the surface of an imaginary sphere with a radius equal to the distance from the satellite. Then when signals from the other three satellites are similarly processed, the receiver built-in computer calculates the point at which all four spheres intersect, effectively determining the user's current longitude, latitude, and altitude. In addition, the receiver calculates current velocity by measuring the instantaneous Doppler effect shifts created by the combined motion of the same four satellites. So, I have already discussed about the working of this GPS. So, in the satellite system, again consisting of constellation of 24 satellites in 6 Earth-centered orbital planes, we only need 3 satellites to produce the location on Earth's surface. A fourth satellite is often used to validate the information from the other. Okay, this way. So as you have seen in this picture, this is Earth, and so many satellites are moving around the different orbits. So there are mainly 3 segments of GPS. First one is space or satellites, second one is ground control, and third one is user equipment. So satellites circling the Earth transmitting the signals to users and geographical position and time of day. Second one is how to control these satellites through ground. So ground control, or you can say a control segment, is made up of Earth-based monitor stations. You have seen in this picture, it may be clear to you. So there are 3 segments. First, this one is control segment, this one is a space segment in which satellite lies, and this one is user segments. That is the user of, or it may be through aeroplane, it may be through plane, it may be through the ship. So the ground control system is made up of Earth-based monitor stations, master control stations, and ground antenna also. So control activities include tracking and operating the satellites in space and monitoring transmissions. So there are monitoring stations on almost every continent in the world, including North and South America, Africa, Europe, Asia, and Australia. Then the user equipment, GPS receivers and transmitters, including items like watches, smartphones, telemetric devices, and all. So in this picture, it is clear that there are 3 segments of GPS. This one is control segment, this one is space segment, and this one is user segments. This is the distance measuring equipment. This equipment is used in aerial navigation, which is used for measuring the distance by converting the time A special electronic pulse take to travel from an aircraft to a ground station and for an answering pulse to return. The airborne equipment displays the information to the pilot. You have seen this thing? This airborne equipment displays the information to the pilot when used in connection with a radio range bearing, which indicates direction. A DME means distance measuring equipment. Reading shows the pilot the exact position of his aircraft. Direction finder, or you can say radio direction finder, radio receiver, and antenna system for determining the direction of the source of a radio signal. A direction finder, which is also known as a DF, can be used by an aircraft or ship as a navigational aid. This is accomplished by measuring the direction of at least two transmitters whose location are already known. When the measured directions from each transmitter are plotted on a map, then the intersection of the two plotted lines gives the location of the aircraft or ship carrying the DF. This technique, using the direction of two or more transmitters, is known as location, is called triangulation. Okay, so because of its early use in navigation, the direction finder was sometimes called a radio compass. It used the navigation aid that has almost entirely replaced by more modern navigational systems, of which the global positioning system, that is GPS, based on satellite communication, is probably the most popular because of its accuracy, low cost, and easy to use. So with the help of this instrument, the pilots detect their positions. So with the help of differential geometry, we can the straight line, which is known as geodesic. We know that a geodesic are the shortest path on the surface. And a surface to be a geodesic if it is intrinsically straight. That is, there is no indefinable curvature from within the surface. The great circles are the geodesics on the sphere. So now the next application is Zermelo navigation problem. This is the most popular problem that can be solved with the help of differential geometry. As I have told earlier that differential geometry has a wide application in navigation also. So let us discuss Zermelo navigation problem, how it works. So Zermelo navigation problem is the real problem of a ship on a sea. So let us consider the surface of the sea to be a two-dimensional space, E2, equipped with a standard norm. In a more general case, the sea can be modeled by a two-dimensional sphere with a natural Riemannian metric. However, in full mathematically generality, the sea can be any Riemannian manifold of arbitrary dimension. So the possible tracks of the ships are curves on the manifold, and it is natural to aim at the destination in the shortest possible time that we want. Okay. So to measure the length of the particular trajectories or the time necessary for traveling these particular trajectories, we use the Riemannian metric and the integral above. Naturally, the curves of interest are geodesics, as I have told earlier. Shortest distance covered by the any is called a geodesic. So let's discuss this Zermelo navigation problem. So Zermelo in 1961 says that if a ship sails in an open sea in calm water and suddenly a mild breeze came up, then what will happen? How can the ship be steered in order to reach a given destination in shortest time? So this problem can be solved with the help of differential geometry, one of the branch of differential geometry, that is Finsler geometry. So this Zermelo navigation problem is quietly related to the geometry of indicatrix of Finsler manifolds. So for solving this problem, let us consider a Finsler manifold for each axis belongs to M in X, which is defined by this relation as phi is equals to y belongs to tangent bundle txm, where phi xy is equals to 1. So let W equal to Wx be a vector field on M. So if we consider a parallel shift to S phi plus W, if and only if phi x comma y minus y f Wx is equal to 1. So further, when this relation is less than 1, then S phi plus W, that is a parallel shift, contains the origin x of Txm. In this case, it is easy to see that for any y which belongs to Tsm, that y over fxy belongs to S phi plus W. That is, fxy satisfies this relation phi x comma y over fxy minus wx is equals to 1. On the other hand, if we take another condition, that is if phi x comma minus wx is equals to 1, then this indicatrix must pass through our origin of tangent bundle. In that case, y belongs to ax, but there is still a unique positive number f, which is equals to fxy, and this unique positive number fxy is called a Finsler matrix with singularity and not regular on total tangent bundle. We call this as this notation f equal to fxy is a conic Finsler matrix. Actually, this Finsler matrix is a regular on conic domain, which is defined by A is equal to union of Ax belongs to Tm. Intuitively, it is natural to meet conic Finsler matrices in studying natural sciences. And in general, we can say that Zermelo find out that the Finsler matrix obtained with the help of these above relations is a solution of Zermelo navigation problem. With the help of these relations, we can find out the smallest path that a ship have to follow to reach its destination. And the second problem is Weber type problem. So in Weber type problem, what we have to do, as you have seen in this picture, there are three markets P1, P2 and P3, which placed at an inclined plane with an angle alpha to the horizontal plane. See it? P1, P2 and P3 are three markets which are originated at a plane S alpha, which is at angle alpha to the horizontal plane. Assume that three car transports products from deposit P to S alpha from market P1, P2 and P3. So what will happen? They move always in S alpha along straight roads. The earth gravity acts on them. The transport cost coincide with the distance from deposit P to the markets Pi. Let us see. So basically, with the help of differential geometry, we can also evaluate the optimized cost of transportation. So the law of above phenomena can be described with relativity to the horizontal plane by means of parametrized functions. So for solving Weber type problem, we discuss a mathematical model related to differential geometry to find the minimum cost of transportation. So we consider a parametrized function f alpha y1 y2, which is given by y1 square plus y2 square over v square root of y1 square plus y2 square plus g by 2 y1 sin alpha. Here g is taken as 9.81. Now since f alpha, that is Finsler space, in which Minkowski space is also involved, the distance measuring the time to arrive from P to P1, P2 is given by this relation Pi is equals to P1 I plus P2I, and the distance formula is given with the help of Finsler matrix by this relation. D alpha P Pi is equals to F alpha, P1I minus P1 and P2I minus P square. And for the converse, it means when we have to reach from these market station to the depository term, then that distance is given by d alpha pip is equals to f alpha p1 minus p1i and p2 minus p2ik. Consequently, we have to minimize the function cf. CF means cost of forwarding from depository to these three markets P1, P2 and P3, which can be obtained by the sum of all these distances, which is denoted by sigma I equal to 1 to 3 d alpha ppi. And from backward process, this is equals this can be shown by CBP, which is equals to sigma d alpha pi to p. First one is p to pi and second one is pi to p. So to minimize points of CF and CV respectively may be far from each other due to the fact that F alpha or D alpha is not symmetric unless alpha equal to 0. But there is alpha, it means there is some angle. So it means the values of CF and CV may be vary. So we will use in general TF or we can say TB to denote the minimum point of CF which corresponds to the point of the deposit when we measure cost in forward or backward manner. So in that case, if alpha is equals to 0, it means if we consider S alpha is a horizontal plane. Just see, if we take alpha is equals to 0, then this S alpha is a horizontal plane. Then if alpha is equals to 0, it means S alpha becomes a horizontal plane. Then the function CF and CY coincide, because the variation of CF and CB is due to alpha, and if we take alpha equal to 0, then the functions CF and CB coincide. Then the minimum point T equal to TF and TB, which is known as Torselli points, corresponding to the triangle. Let's see. We have prepared a triangle joining these three markets P1, P2 and P3, which is given by f naught y1 y2 equal to y1 square plus y2 square upon v. So this corresponds to the standard Euclidean matrix. Indeed, d naught p comma pi or d naught pi comma p becomes equal if we take alpha equal to 0. And this can be evaluated with the help of this relation, which is given by under root p1i minus p1 whole square plus p2i minus p2 whole square divided by v. Measures the time which is needed to arrive from P to Pi or vice versa with a constant velocity v. So in this way we can see that with the help of differential geometry, with the help of the making models related to differential geometry, we can also evaluate the minimum cost of transportation as well as navigation data and so on. So the basic conclusion of these areas says that differential geometry is not a separate mathematics field. It brought different fields like PDE. We can use it. You have seen that we can use PDE, algebraic geometry, algebraic topology, and many also others. So with the help of differential geometry, we can evaluate the navigation data, we can evaluate the position of missing aircraft as well as missing ships also, how to reach the minimum data, how to reach the position of a missing elements in space as well as in water, how to reach the shortest route to achieving the destination, how to minimize the cost of transportation. All these fields included differential geometry. In this way, we can say that differential geometry is everywhere. Where there are shapes, geometric structure, there is differential geometry. These are some references. Thank you. Is there any question from our participants? You can ask. Yes, is there any question? Yes, sir. Am I audible? Is there any question, sir? You can ask.